right? And we're not going to do, and as I said, I took an entire course on this topic from my father. And so he spent much of his life on this problem, right? So we could do a lot on it. And we're not. We're going to have, instead of multiple sources, we're going to have one source, we're going to have one sink, and we're going to have one commodity. All right? So that makes it easier. So here, what's the problem? Is the input is a directed graph, could have cycles and stuff, and each edge, you think about each edge is a highway or a pipe that can carry your commodity. And each edge has a capacity, and the capacity is how much of that commodity can flow per hour, right? It's a capacity, right? And we'll have a source node, right? Here I got it's amazing what you can get off of the internet. Here's a source node that feeds the system, right? And we have a single sink that lets the flow out, right? So this is our factory producing the water. Here's our sink absorbing the water, and we want to get as much flow from one end as the other, right? And so our goal is max flow. Here's an example of a network, right? And I haven't talked about solutions yet. I think we'll talk about it in a minute. Here we're just saying, look, it's not even clear which way the water should flow, right? It can be really confusing. So we're going to say for some UV pairs, there might be a pipe in both directions, right? But as you know at home, your upload speed is different than your download speed. So we're going to have, our graph is going to look like this. If you want to flow this direction, you can flow at this speed. And if you flow back, you only can flow at that speed. And one thing we're going to, another requirement, it's not a requirement, but it would be stupid to do otherwise. Let's not have water flow in both directions, because that doesn't help anybody do anything, right? So water will only flow one direction or the other in each, right? All right, so, all right, so we're now talking about a solution. So what is a solution? A solution tells you for every edge how much is flowing through it, right? So this picture, you should learn what it means. It means that 75 is the max that you can go this direction, and we're currently going 15 in this direction, right? And in this direction, you could go 10, but we're going 0. Why? Because we're going the other direction. Everybody buy this? Or you could be going the other direction, right? There's another possibility. All right? Yeah? Well, it's silly to go around. Our goal is to get from S to T, so let's not do little spirals, right? So what's the solution? As I said, for every edge, I tell you the flow from U to V. And one of the requirements, in order to be a valid flow, we have various requirements. The one requirement is that the flow from U to V doesn't exceed the capacity from U to V. That's obvious. The other thing we're adding here is that the flow is going to be 0 in at least one direction. Now, before we go on, many places that this is written up, like in Corman, what they'll say is if the flow from U to V is 15, then the flow from V to U is, no, they're going to say something different. Negative 15, right? Because I could be walking this direction means I'm walking this direction backwards, right? And this concept is going to come up as we talk about this topic. But the reason I'm not going to do this, but I'm going to put a 0 here, is actually because it makes it harder, right? And it's not that I want to torture you. It's because when you do the negative here, then the math becomes slipperier. It becomes, you can just hide things in the math that I want to point out. All right? So we're not going to do that. We're going to have this requirement. And then, all right, that says some text will do the negative. And now we have another requirement that that the graph doesn't have any leaks. You know, water doesn't leak out, and water doesn't just appear from nowhere, right? So how are we going to do that? Is we're going to say for every node V, right? Now let's focus on V. Let's take the total flow coming in. What's that? That's the sum of overall, this is V, the sum of all U's of the flow coming in, right? It has to equal the total flow going out, right? Does that make sense? And actually, if we had negative flow, then that's one place where the math gets easier, right? Because some of these are positive and some of them are negative, and they'll add up to 0. Right? And the exceptions to this are your source and your sink. They won't add up to, they won't balance out because the source is providing and the sink is letting go. Right? So now, if we have a valid solution, we have to measure how good of a solution it is. And how good it is how much is flowing from S. So you might say it's the sum over all U of what's flowing out of S. Right? Does that make sense? But it's not completely good enough because if anything flows back in, then that's not doing us any good. Right? That's just going in a circle. So we're going to, our rate of flow is going to be what's flowing out of S minus anything that comes back to S. Right? So things that are going in a circle cancel out. Everybody get that? Right? And now, later, we're going to prove that because no water is being produced or being drained anywhere, that this actually equals what's flowing into T minus what's flowing out of T. Right? In fact, one thing we'll prove is that if this is our graph and this is a cut, and we're going to define cuts later, that the rate of flow is going to equal, is always going to be the sum of what goes this way minus the sum of what comes back. That will stay a constant. One thing we'll prove is that's a constant for every cut. Everybody kind of buy that? Any questions? How much time do you have now? 6 minutes. 6 minutes. It's amazing what we can cover, isn't it?